Substitution rule, part 2. And I've called it part 2 because it's going to include not the obvious U-subs, but the U-subs where you have to break the rules. They are exceptions to the major rule. And I've got a whole load of these guys here. And they're so different from each other that I can't like say, okay, here's 2 and they all look the same. They all have their own little idiosyncrasies that you have to be aware of. Now, let's take, I'm sure got this window in the way, right? Let's take this guy. Now, if it was a fraction, the typical U-sub would be the bottom, but you know that's not going to work. And so one of the exceptions is, if you ever see a natural log, make that your U-sub. So let's see how that works out. If you differentiate with respect to x, what do you get? What is the derivative of the natural log of x?
1 over x.
Correct. Now, if you do the crossover, and then in this case, multiply both sides by x, you get to the stage that I call you isolate the dx. Now we can come over here and you shall see what happens. Well, the log becomes u, so u to the 10. The x on the bottom stays put. The dx becomes an x du and cancelled. So the original integral now becomes this guy, which is a simple power rule. Add 1 to the power, divide by the new power. Return the log, instead of the u, return the log x. And don't forget, you get a plus c going on. So if you see an integral and there's a log x in it somewhere and you know you're going to do the substitution rule, I think the candidate here would be your log x. Now, another fraction that breaks the rules. Normally when you've got a fraction, don't you pick the guy in the bottom? That's one of my rules, right? When it's a fraction, pick the denominator. Don't I have another rule that says if it's a cosine or the sine of an ugly guy, you pick the ugly guy inside? So here's the question. Is it x to the 4 or is it pi over x cubed? Because it's one of those, but it can't be both. Pi over x cubed or x to the 4? What would be your gut feeling for the U-sub? It's okay to get it right.
Pi over x.
Okay, it's okay to get it right as well. Pi over x cubed. Now, I'm going to rewrite that as pi x to negative 3 so that when we differentiate with respect to x, we can use the power rule of differentiation, which is multiply by the power and reduce the power by 1. And I'm going to call this guy that fella. So when we do our little crossover thing, we have x to the 4 du and negative 3 pi dx. And then divide both sides by, I guess, negative 3 pi, which I'm going to call negative 1 over 3 pi x to the 4 du. So we isolate the dx, and that shouldn't be there. So dx is this fella. Right, come over here. The cosine of pi over x cubed becomes the cosine of pi. The x to the 4 is going to stay put for a minute. And nobody has noticed my mistake. What is my mistake in this line? This line to that line. What did I do wrong?
Should be x to the fourth over 3 pi.
Yes. I said divide both sides by negative 3 pi, and then I didn't do it. Right, that's what I did wrong. I'm going to put on mute because if I hear any more yawning, I'm going to fall asleep. So, you hold off for a second. It's been a long day for everyone. I can understand that. Okay, let's continue with this question then. Ah, I've lost you. Where have you gone? I lost you. I went and moved the window and you disappeared on me. Shows you how tired I'm getting. Ah, there you're back again. How on earth did that happen? Right, there we go. Things are not going smoothly for me today. There. Okay. Third time lucky. Now the dx became negative x to the 4 over the 3 pi du. Now the reason I recognize that I made a mistake there is that don't you typically get the x's cancelling out round about this line here. So in this case, this will cancel out with that. And I'm going to be looking at negative 1 over 3 pi cosine of u du, which I can then integrate. And the antiderivative of a cosine u is a sine of u. And then I can return the u by replacing it by that. And don't forget your plus c. Are we okay with that particular question?
I think so.
Okay, good. So just when you're beginning to maybe say, okay, it's not the worst thing in the world. Here's one that is probably one of the worst things in the world. And it's the worst thing in the world because there are so many choices out there, but typically only one of them works. And the correct answer in this question isn't always what you think it's going to be. I'll give you an example. That's one version, and I'm going to give you a different version. And show you what one little change. Have you noticed that the 40 is not that important, right? That could be any number. So, but I just decided to call this one to make it a little bit easier. On the bottom, I've got 1 plus cos squared and a sine x on the top. And over here, I've got 40 plus cos squared x and a sine, good grief, 2x on the top. That change, that x becoming a 2x, totally changes your u sum. One of these u subs is cosine x. One of these u subs is the entire bottom. If I look at this one and I think, well, what do I want? Do I want just the cosine x or do I want the 1 plus cos squared x? What you kind of have to ask yourself is, what's the derivative of cosine x going to get me? And the answer is it's going to get me something to do with sine x, which is why this one is cosine x. And why this one is 40 plus cos squared x. do this one first, slightly out of order. If you differentiate with respect to x, be careful. What does the derivative of a cosine get you?
Negative sign.
Right. So the crossover looks like this. And then you can divide both sides by that fella. Over here, I'm going to have sine x. 1 plus cos squared becomes 1 plus u squared. And the dx becomes, the dx becomes negative 1 over sine x du. And you get your little cancels. And then you end up with negative 1 over 1 plus u squared du. Now, hopefully, you've seen a few of these, enough of these to recognize that that is a doable integral. What is the antiderivative of 1 over 1 plus x squared, u squared, whatever letter of the alphabet they're using? What's the antiderivative of 1 over 1 plus u squared?
Inverse tangent.
And then always remember to return back to the original variable. So this particular integral, that's its answer. And this one, the entire BOM, which is kind of the normal rule. You know, if you see a fraction, pick the BOM. Not so nice. Well, differentiating 40 is easy. You get nothing when you differentiate a number. But cos squared x, basically that guy, right? Then isn't this the derivative we call the chain rule? So you multiply by the power, reduce the power by 1, and then you differentiate the cosine of x, and that gets you negative sine x because you differentiate. So that becomes negative 2 sine x cosine x. Does anybody recognize a trig identity for 2 sine x cosine x? What's it equal to?
Sine 2x.
Yes. And since there's a negative in front of it, it's going to be the negative of sine 2x. Now I can continue. I'll do the crossover. And then I will isolate the dx. So we now have the integral of sine 2x over u times negative 1 over the sine of 2x dx. These guys cancel out, and we get that guy, which is negative log of u, and that can return back to as long as they're not too complicated. This step here is about 5 steps. Your U subs can sometimes be almost as much work as this. At least a typical U sub is guaranteed to have 4 lines in it, you know, this bit in red. And you might get 4, 5, or 6 lines here. depending on how ugly the integral is. Any questions about that guy, that particular one?
Yeah.
No, we good? Okay. I'm gonna have to open another window here as if I haven't got enough windows already. And we're going to have a look at okay, why didn't that update? Are you looking at section 5.5 substitution rule part 2? Is that what you're saying?
Yes.
Okay, good. So, right, let's see if I can make that bigger. Should be able to. There we go. So let's look at some more of these unusual U-subs. Question 4, the U-sub is not 1 plus x to the 16. It's not the denominator, which it typically would be 9 times out of 10. Any suggestions for what the U-sub in question 4 would be?
X to the 8th.
Wow, I wasn't expecting that, and it is correct. Now, the answer might be, well, I've already done integration before and I remember it, but how do you know that that's the right one? Was there any clues in the rest of the question that kind of made you think, oh, x to the 8 is going to work well with this big thing? What made you think
It
that
was like
answer?
the 1, it turned into 1 over 1 plus x to the squared, which is inverse tangent.
Right, and the x to the 8, when you differentiate it, would get rid of the x to the 7. That also be part of that. Okay, let's show you it working then. If someone gives you an antiderivative that just looks like that. Now you might say, well, why couldn't I pick 1 plus x to the 16? Because that works lots of times. Well, if you differentiate x to the 16, won't you get x to the 15? Do you notice that there's no x to the 15s anywhere? It's not going to work. But if you pick this guy, which for some reason has stopped being read, then the derivative with respect to x is going to be this, right? Multiply by the power reduced by 1. Then you do the crossover. And then you can isolate. And the good part is, do you see that x to the 7 there? He's going to kill off that one. So it's going to be the integral of x to the 7. Instead of a dx, it's going to be 1 over x to the 7 and a du. So they're going to play well together. Now the 1 plus x to the 16 becomes 1 plus u squared. Because isn't u squared, if that is what u is, isn't u squared twice as many of them? Now when you cancel these guys out, you now have that integral, which is a really pretty integral. And we know that's an inverse tan because we've seen tons of them now. And then we return back to the original. So if you come across some integral and you're thinking, who should I pick? If the obvious one didn't work, because very often you sometimes have to try the obvious one and then say, oh, that didn't work. And then you go hunting for the weird ones, because 9 times out of 10, the obvious one will be the right one to pick. Well, I would try the obvious, 1 plus x is 16, didn't work. And then I might try x to the 7, doesn't work. I might try x to the 16, doesn't work. And then I might eventually hit the right guy. So that would be a kind of trial and error process. But what happens is the next time you see a fraction that looks like that, where this guy and that guy are totally different, but you know that if you make this 8, you'll get a 7 out of it, you'll think of choosing this as your u sub. Now, I'm going to return now to the homework sheet page. What would the u sub be in question 5?
Guessing the top.
What part of the top? It is to do with the top, the right answer.
Thing.
Can't hear you, your voice broke up.
I thought it would be the whole thing.
Ah, well, if you, ah,
Would you just use the exponent?
what would you just use the 1 over x to the 4? The 1 over x to the 4 I know will work, but e to the 1 over x to the 4 would also work. So there's 2 correct answers there, which is very, very rare. U equals 1 over x to the 4 would be the standard answer, and that's perfectly fine. That's a good answer. That u sub will work. But u equals e to the 1 over x to the 4, that also works. And the reason why that works is it's a very messy chain rule, but it works. So I like that one. The next one is so easy, it's hard. It's a contradiction, but it is. It's the integral of x over the square root of, in this case, x minus 8. And there isn't really a choice here, mostly because there's so little in the thing, there can only be one u sub. That's the easy part. The easy part is there can only be one u sub, right? You can't make u equals x. Okay, I take it back, there could be 2. It could be the square root of x minus 8, or in fact, the one that you should use is that. So the u sub is the easy bit. The next bit is what makes it so difficult. Well, let's go through it and see what happens. Differentiate with respect to x, you get 1. And the crossover, boom. Didn't even read 4 lines. That looks nice. So where's the problem going to happen? Well, here it goes. We have an x, we have a square root of u, and the dx just becomes a du. That's where the problem is. There's an x. There shouldn't be an x. That x should have cancelled out with some other x. That's what happens in these things. That x shouldn't be there. All that should be there is u's. So how do we make it happen? How do we find x in terms of u?
Can we set u equal to x and then substitute for both of them?
Sounds like a plan if I picked you up right. So I'll put a little squiggly line here. We're going to take this guy and rearranging it, we can now get x in terms of u. I hope that's what you meant. And so this x becomes u add 8 And this square root becomes u to the half du. Now, everything is in u's. And you might think, God, that's just as ugly as everything in x's. What have you done? You've just made my life different but ugly, and I can't do it. Ah, that's not true. You can do this. What should I do next? What should I do next?
Distribute the u.
Yeah. Now, since we have tons of things to do, I'm going to do my little ... thing, which basically says is, could you finish that question off in the usual way, right? Power roll, add 1 to the power, divide by the new power, turn all the, make it look pretty, and then turn all the u's into x minus 8s, and 1, 2, 3, 4 lines later, you've got it. But if you can get it to that stage, you've pretty much broken the back of that question. So there isn't a single special part 2 u sub. There are lots of special part 2 u subs. This one, again, I'm only going to start it, give you an idea of what u sub we should use. What I hope will happen is that the more you do, the more you see, you start getting an inkling for how this works. This one, by the way, is similar to the question 9. What do you think the u sub for this one should be? You've already done one quite similar to it.
Is it the 1 plus cos squared? Can't remember.
Ah, it wasn't that one, but it was the other choice. Remember, one choice says use the whole bottom, and the other choice says just use this little guy, not the square part, but just this guy. This one was this, like this one. Now, if I take the cosine of 9x, would you agree that you're going to have some version of 9x up here, sine 9x? That's why that one works. So I'm going to differentiate with respect to x, this fella. And differentiating a cosine gets you negative a sine. So it's negative sine 9x. Because it's a chain rule, times the derivative of 9x, you get that guy. The crossover gets you that guy. And then when you isolate it, when you isolate the dx, you get that guy. So this becomes the integral of the sine 9x. The 1 plus cos squared becomes 1 plus u squared. And the dx becomes this fella here. Oops. So you get negative 1 over sine 9x du. They cancel out. And you get that guy. Do we know how to integrate that guy?
Inverse tangent again.
Yeah, inverse tan and ... off you go. You need to, whatever the word is. I'm not going to do question 10, but we'll talk about who his u sub is and a little bit about how you would fix an issue that would happen later in the process. It might not look like it, but we've actually done a problem that's got a similar situation. What do you think the u sub in this question should be? And that's the easy part. There are not a lot of choices here. What would your u sub be if it was kind of just an obvious thing, something not too difficult?
2x plus 7.
Yeah. Now, if you do the derivative with respect to x, you get 2. Can you remember that x square root of whatever it was, x plus 3 one? Remember that one? This is really a very similar situation. Doesn't look that close to it, but mathematically it is. Now what you're going to have is an x left over again, a u to the 8 and a half du. And just for completeness, to make it look pretty, you got that. And there's your problem. Don't you have an x left over? Just like we did in the integral of x, square root of x minus 1 guy. What is that x going to have to do? Well, it's going to have to become a u. And so you start with this fella, and you use this to find out what x is equal to on its own. So as long as you do it to both sides, it's okay rule. So I'll subtract 7 from both sides. I'll then divide both sides by 2. What does that get me? That gets me a half u, take away 3 halves. So I have a half u, take away 3 halves. Okay, what would I do next to get this to the place where I can start integrating? Because right now it's not quite there, but it's like one line off it. What do I do next?
Distribute the half.
And everything else, I'm assuming, yeah. So a half in this and this and this. So that times that gets you a quarter u to the 9. And that times that times that gets you negative 3/4 u to the 8 du. Right. Do you see that you can now do the power rule on these? You know, add 1 to the power, divide by new power. And then once you got all your answers with u's, turn all the u's into 2x plus 1's and you're finished. Almost finished, these guys. 11. This is like the third version of the same kind of situation. They all look a little bit different, but they're really the same situation. What do you think the u sub's going to be this time?
X squared plus 7.
Right. Is that getting a little bit easier to recognize when you have to do this particular u sub in this story? We take this guy, you differentiate in respect to x, and you just get 2x. Nothing wrong with that. I mean, this part here is pretty much what you do every time, right? Now, over here, I have an x cubed. I have a square root of this guy becomes a square root of u. And the dx becomes this guy. Now, in a normal simple, if there is such a thing as a simple u sub, wouldn't these guys cancel out and you'd have some version of the square root of u to deal with? But not this time. There's only one x, and that makes x squared left. So we are left with 1/2 x squared, the square root of u. Same problem. That's what makes this one of the three versions we've seen today. There's an x or an x squared or something like that left over, and we have to figure out how to turn that into u's. So you go back to your u sub and you use it to figure out what x squared is in terms of u. Actually, it's not that bad, is it? Isn't x squared just u over u minus 7? So this becomes u minus 7. This becomes u to the half. We've seen this happen a couple of times today as well, haven't we? Where we have an expression that looks like this with u's in more than one location. What we do, distribute. A half times u times this guy gets me 1/2 u to 3/2. A half times this, negative 7/2 u to the half du. It's about halfway through, right? Power rule. Add 1 to the power, divide by the new power. Finish your question off by replacing all the u's with x's. And that's pretty much the end, except for one question. And this one question is a one-off amongst a whole load of one-off questions. It's even more unusual. And it's not because it's a u-sub problem, which is typically the questions that we've been doing today, right? Unusual u-subs and how you deal with them. What we're looking at right now is an ugly fraction. And what the mistake people do, because it's normally not something you wouldn't think about doing, because you don't need to, is that you don't realize that to solve this question, you have to solve two questions. You have to split it. Now, this piece here, I'm beginning to think the inverse tan's the only antiderivative we ever use, because isn't this just an inverse tan? It did not need a u-sub. On the other hand, I want to find this fella, right? This is a u-sub, isn't it? Who's the u-sub in this question? What u-sub should you use? Oh, we've done so many weird u-subs that the obvious u-sub has kind of left the building. This guy is not a trick u-sub. This is an obvious u-sub. It's one of the 90%ers.
1 plus x squared.
Yeah. Because you've seen so many situations where it isn't that, do you see how you're hesitating now? I can understand that, why you would do that. Right, you differentiate, you get this guy. If you do the crossover, you get that guy. And last but not least, you isolate the dx. So this fella becomes 9x over u times 1 over 2x du. And the good old fashioned everybody cancels the way they're meant to happens. And we get 9 over 2, 1 over u's. I prefer to write it that way, right? The 9 over 2 and the 1 over u separately. Antiderivative of 1 over u is the log of u. And return the u back to x's. And then you can just stick it up here. And that's you finished. So we have we've done a lot of different situations that require the u sub. There's the straightforward u subs like this. There's the u subs where it's obvious what the u sub is, I think. Once you've done enough of them, it becomes obvious. But the problem is there's going to be an x or an x squared left over. And we've also looked at u subs, especially ones with trig in them, where the u sub isn't that obvious. You have to go looking for it. It's hidden in there, but you have to go looking for it. And you also get those kind of hidden ones in fractional u subs. And that takes care, I hope it takes care of, u subs. Right, any questions on u sub before we start our next section? Are we good as good's going to get right now? Ready to move on then? Give me a few moments to set myself up here. That goes away. Oh, I ran out of time. I'm having to log back into Cengage, that's why we're waiting just a tiny bit extra time. Okay, go into that guy. And we're starting the new chapter today. And it's chapter 6. So get myself set up here. And let's do the notes, the intro. Ah, darn it. Hit the wrong button. Try that again. Okay. Area between curves. So we're doing an application, a use of finding integrals. So I'll show you what the problem that this one solves. Imagine I have a curve called y equals f of x. And I have another curve starting at the same point, finishing at the same point, but called g of x. And this guy here is x equals a, and this guy here is x equals b. And the area between the two curves is this area here that reminds me of a fish, right? It looks a bit like a fish, right? That's what we're trying to find. The area between two curves, f of x and g of x. And this is how you do it. It's the integral from a to b of f of x, take away g of x. Well, that's amazing, isn't it? I mean, that's very simple. The area between two curves. Now, when you're looking at the area between two curves, the reason I'm hesitating, apart from the fact that I'm totally distracted today, Good. Now, come back. I'm not able to put my windows in the right place today. And for some weird reason, it's moving and I can't get to see you and have my white paper at the same time. And I want to be able to do both because it helps me see if you're understanding stuff. But evidently I can either do this or I can see you, but for some reason I can't do both. So anyway, you're thinking about how this area works. Let me tell you a couple of things about this area before we go any further. This is a physical area. It is not a net area. So this area is always positive. It's never going to be negative. Secondly, although it's pretty obvious because I've written it down, there is a choice here. They might just say to you, find the area between f of x equals x squared and g of x. Well, they won't even call them f and g. They'll say y equals x squared and y equals x. And if you are given that, you need to know which one is the top and which one's the bottom. So the way I do that is plug it into your calculator and have a good look at it. And then imagine a random vertical strip. And that guy's the top. And that guy there's the bottom. And whatever guy is up here goes there. Whatever curve goes in green goes here. So let's give you an example of that type of question. Suppose you wanted to know the area between y equals x squared and y equals x between x equals 0 and 1. What I would do in step 1 is I would plug these two guys into my calculator. So let me show you that happening. And the reason I would do that is unless I'm really good at knowing what curves look like in my head, or that I can sketch them in my head, you know, without even physically doing them. You go here and you go, okay, y equals x squared. And then you put y equals x. And if you just do a window, I wouldn't do anything even like that. If you do a window from 0 to 1, and then you just do zoom 0, there's x squared and there's the x. Can you see now that what you've got is a visual representation of the two fellas? So you've got one of them's a curve and it's y equals x squared, and the other one is a straight line. And the straight line is y equals x. And the area between them is a little banana. Why is that helpful? Well, let me show you how I would set up the integral to calculate the area between them, that little banana. The area between them would be the integral from 0 to 1. If you imagine my little vertical strip there, isn't the straight line the top guy and the curve the bottom? So it's x, the straight guy, take away x squared, the one underneath. And that's the integral that would get me the area of that little banana shape. So that would be the integral from, well, I don't need to do any clever math. Power rule. And then do it from x equals 0 to 1. And that would get you a half, take away a third, minus a whole load of nothings. And that is a sixth. I'm not going to do it, but what do you think the answer might look like if I just did them the way the question phrased them? So I made this guy my first guy, my f of x, and I made this one my g of x, right? So I did this. What do you think this integral would give me? Any ideas?
Sorry, I missed the question.
You switch. Yeah. What would happen if you switch places, right? Instead of going x take away x squared, you went x squared take away x, right? What do you think the answer would look like?
Would it be negative?
Yeah. So if you ever do an area between two curves and the final answer ends up being a negative number, you're wrong, right? The answer is not correct. It could be wrong for two major reasons. The first one is you just screwed up algebraically, right? You put in a number and you squared it and it wasn't squared right. And that can happen. But the second one might simply just be you put them in the wrong order. So if that's the only mistake you make and you put them in the wrong order, you get the same number, you just get a negative version of that number. So areas are always positive, right? The area between two curves are always positive. That's the first thing you make sure of. And the second thing you make sure of, and that's where step 2 comes in, is you make sure you identify who's going to be the F and who's going to be the G. Right? Who's going to go first, subtract who's going to be second. If you can get those two things sorted out, most of the integrals you're going to do are not going to be that bad, right? They'll not be hugely ugly. They'll be, I hope, pretty doable. Any questions so far about how to find the area between two curves? Are we good?
So far.
So far, good. You are allowed, remember, you are allowed to say, nah, I don't know why this is working, or that don't make sense to me. It gives me a chance to, well, hopefully, show you how to do it. Okay, well, let's do some more examples. I'm doing areas between curves of the typical f of x kind, but I'm going to be switching them in a little while because there are other more complicated versions of these questions that we need to deal with. So this one here is a version of question 10. And it's the curves that we're trying to find the area between is 9 cosine of pi x, and the other one is 8x squared take away 2. And let's suppose I'm only interested in doing this integral from x. Oh, it's going to be some kind of negative a quarter to plus a quarter. I'm making up my own version. Right? One of these guys goes first, one of these guys goes second, right? The limits integration, if they tell you what they are, then that's one less problem. There are two distinct possibilities here. Couldn't the area between the curve be this guy, take away that guy? Or couldn't it equally be this guy, take away that guy? Agreed? Somebody goes first, take away somebody goes second, right? F take away G, F take away G. The math of these will look very similar. The answers will look very similar. Now, I'm not telling you the answer because I haven't done it yet. But can you imagine I did this guy and the answer ended up being 3/4, and I did this guy, it would be -3/4. How would I know which one of those was the right one if I ended up doing both because I couldn't figure out who to go first and second? How would I know which one of these was the correct answer?
If
Positive.
it's positive.
Yeah, it's positive. Now, I'm not telling you to do this as a strategy because it isn't a good strategy. I'm not saying, just do both versions and then the one that's positive is the answer. Because you can imagine that just doubles your workload. So let's show you. Let's do it a different way so I don't need to go in and out so many times. I don't know if that's the right one. Let's check it out. Go into a calculator. I'm going to clear out all these guys. And then just type in 9 cosine pi x. I'm making no commitment yet to who is going to be the first one, right, the top one. And then the other guy is 8x², take away 2. Choose the window that they have given us. So what, -1/4 to +1/4. And then just do my zoom 0, which is zoom to fit. It's my favorite zoom. Now, that guy there is 9 cosine pi x. And this guy coming along the bottom is the 8x² minus 2. Cosine 8x² minus 2. Now, if you say, well, I can't tell looking at them that that's who you say they are. So watch this little trick. If you go to your calculator, TI-84, and you move the cursor to the end, if you hit enter, do you see how that's flashing thick? If I move off it, you might see it a bit better. Now, what that has done is it says to me now that the thicker curve is the cosine one. So now when I graph it, can you see that's the cosine curve? It's the thick one. Can you see the skinny one is the 8x² guy?
Oh, that's cool.
Right? So if you are, because two curves might just look like two curves, I still don't know who's what. Make one of them thick, and you know that the first one you typed in is a thick one, and that'll tell you the answer. Now, suppose, excuse me, I'm trying to think of another situation here. I think that's probably we covered a single X above and below, so I'm just going to make up one with much nicer, easier numbers than that one, just to, you know, just as a complete. So let's suppose we had y equals x², and we had y equals 2x plus 1. I'm going to be doing something to this in a minute. So at 2, about 6, x equals 0, 2, check that's on 2, 2, 8, 2, 4. That should work. Okay. So the question was, find the area between y equals x³ and y equals 2x plus 4 from x going from 0 to 2. Anybody got feelings? Which one of them do you think is going to be the high one? The one on top? Anybody got a gut feeling for it? Which one it is?
Would it be the 2x plus 4 on top?
I don't know is the short answer. My gut feeling is yes. But sometimes my gut feeling plays tricks on me. Right, so I'll take that slowly. I've typed in x³, and I've made that the thick one. And I've typed in 2x plus 4, keep my fingers crossed that this works, on the bottom one. I went to my window and did 0 to 2 because they told me. And I did, or I'm about to do zoom 0, which will draw it. And the 2x plus 4 is the straight line, and it's a high guy. So if you imagine my little sketch, it looks something like this. And the straight line is 2x add 4. And this fella is the x cubed. So the integral between 0 and 2 of 2x plus 4, take away x cubed. Integrate that, power rule on that, and integrate x cubed, evaluated at 0 and at 2. So the area between the two curves looks a bit like a boat. Well, to me it does. So what do? I plug in 2. So it's 2 squared, 4 lots of 2, take away 1/4 to the power of 4. If you know everything's zeros, just say take away 0, so you don't have to write down nothing squared plus 4 nothings and so on. That guy's 4, that guy's 8, that guy's take away 4. Oh, and the answer is 8. So this is just the beginning of area between two curves. But, oh, there's my little rectangular strip. Can you see the straight line up here and the curve down there? Suppose you're doing a test or a homework question and you get that answer. You know you've done it the wrong way around, agreed? Well, you're assuming that everything else you did correctly. That you know you've done it the wrong way around. How can you fix your homework so that you don't end up having to redo the entire question? What would the right answer be if this was -10?
10.
Yeah. So you can fix your homework. And the reason you can get away with that, in WebAssign, don't they just want the answer? For most questions, at least, right? So I'm just giving you a little safety net. Hopefully you will plug it into your calculator. You'll make sure you can tell who the top and bottom is. So you can make sure you put this guy on the top first, take away this guy on the bottom. And then the integration that you get to do, at least the ones we've seen so far, are not that bad. They're not anything as horrible as, you know, the U-subs that we've been doing, right? They're a little bit nicer. Power rule is probably going to be one of the major techniques that you would use in many of these questions. But we've only done one situation here. And that is two given curves with a start and a finish value, right? Nothing too special. Here's another situation. This one is not a little different. I would say a lot different. And we're still finding the area between the curves. But the difference is that these curves are not y equals x cubed and y equals x squared. These curves are orientated in terms of the y variable and the y-axis. So these curves will be called x equals y cubed and x equals 2y plus 1. The area, when they do this, is the integral from c to d f of y, take away g of y, dy. So, I mean, if one of them was y cubed and the other was 2y plus 1, it would be y cubed, take away 2y plus 1. Now, in mathematics, we like x's, but isn't it okay to integrate with any letter of the alphabet you like? Can't you do, we've done them, haven't we done dw's and dt's, and I think we did d thetas even, right? So what's wrong with dy's? Nothing. And what it tells you is the area between these two curves. But the orientation does make it a little bit trickier. When it was vertical like this, it's easy to tell who's first and who's second, right? Who's on the top, who's in the bottom. When they go this orientation, the typical strip that I use will be a horizontal strip. And the guy that's here goes in the top, and the guy that's here goes in the bottom. So the curve that is furthest to the right goes first. Now that makes quite a big difference to the process. It's much more difficult to figure out who goes first and who goes second, because you can't put this into your calculator, right? Your TI-84 is only being designed for y equals x cubed, right? Y equals 2x plus 1. Y equals a function of x. You can't type into your calculator x equals a function of y and see it. So that will be a bit of a problem. So what would these questions look like? Well, you might be asked to find something like this. Find the area between x equals y squared and x equals y plus 1. And y's are going from 0 to try to make this curve work in my brain here. I need a number. Okay, I'm going for 1 and I may have to change that. I've got the same problem I'm trying to describe to you. I'm trying to imagine what these darn things look like, and it's very hard for me to visualize it. So wouldn't it be nice if there was a way we could sketch these so we can do step 1? Now, I said you can't do it on the TI-84, which is true, you can. But with a bit of luck, I should be able to find Desmos. Have any of you ever used Desmos in another class?
Yes.
Yes.
Cool. Right. So if you've not, then this is a quick tutorial on how to do it. I have a link to Desmos in Canvas, which is what I basically was just doing. And it's here. And if I click on it, we got this. And I should be able to type in x equals y squared. There, you see it in red? Now, enter. And x equals y plus 1. There you go. And we're interested from 0 to 1. Okay, I got my picture. I'm going to do a very basic sketch of what I can see. And I'll now return. So basically, you just say X equals the first guy, X equals the second guy, and you'll be able to see a picture. Now that picture is helpful. Can I do this a little bit bigger? Yeah, good. Now, the area between the curve is here. Is the blue guy going to go first? Is that going to be like my f of my f of y? Is the blue guy going to go first or second?
First.
Agreed. So let's now go into my little thing and show you that. Actually, if you've got Desmos there, you probably don't need to do the physical picture, but if you keep notes, this would be helpful. This is 0, and this is roughly where 1 is. So my area between these two curves is the integral from 0 to 1, because they told me, of the straight line first, take away the curve second. And that becomes the integral from 0 to 1 of that guy. And that becomes the integral from, well, I don't need to do any more integrals because I'm ready to do power rule. Now, you plug in 1, you get a half, add 1, take away a third, plug in 0, you get a whole load of nothings. That guy and that guy and that guy play well together, you get 7/6, I believe. Now I'm going to see whether or not I can count. 1/2, add 1, subtract a third. Hit the math button, choose option 1, and it's 7/6, so I got it right. So, draw a picture. Why do you need a picture? So you can see who goes first, who goes second, right? Who goes top, who goes bottom, or who goes right, who goes left. Right? Left. Again, all that. How are we doing? We cool? Two kinds of areas, up, down, left, right. When it's up, down, it's y equals x cubes and x squareds that you're dealing with, and left and right, it's x equals y cubes and x equals 2y plus 1s, at least the ones we've done so far. So, single curve, whoops, better go back to pointing at things. Single curve, top and bottom, area between given. Single curve, left and right, area between given. So what more can they do to give you different versions of this same kind of question? Here's one. This is basically question 3. We have x equals y squared take away 3, and we have x equals e to the y. This one's actually nice because they've given you what would be a Desmos picture, right? So you can actually see it. And you're being asked to find the area between the shaded regions. So let me just show you what that guy looks like. Yeah. Now, do you see how it's how everything you need to know is actually on that picture? And so we need to set up the correct integral to find that shaded blue area between those two curves. So the y values go from -1 to 1. So that's what I'm writing down. And can you see that it's an e to the y because it's to the right? Take away a y squared minus 3. So it's going to be an e to the y, take away of y squared minus 3 dy. Now from that picture, this is the integral that I've managed to set up. And I am now about to do a deliberate mistake. This is the integral of e to the y, take away that guy, take away 3 dy. Deliberate mistake. What did I go and do wrong?
Distributing the negative sign?
The correct answer is that. Now, can you imagine that these are eventually going to have maybe 2, even 3 pieces to it, and so will this one. And so when you take the first guy and you subtract the second, try and remember that you're distributing the subtraction throughout all the terms. Now, this fella here is pretty much good to go, isn't it? There's no anything really messy as far as the integration goes. So integrate e to the y, you get e to the y. The power rule for the next term, and the 3 gets me 3y. And then you can evaluate it. Yeah. Well, I'm taking this one to the end because there's another little kink in the tail at the end. And this is in the substitution. Right? You get e to the 1, take away 1/3 times 1 cubed, plus 3 times 1. So that's the first guy. Subtract e to the negative 1 minus 1/3 negative 1 cubed plus 3 lots of negative 1. E, subtract a third, add 3, take away e to the negative 1. Negative 1 cubed is negative 1, times that makes it plus a third. And negative 1 gets you that. And you can do that more than one way. I'm just going to take it the slow way. There they guys. Take away the guy, take away that guy, take away that guy. So you notice you're taking away all 3. And these guys, eventually you add them together and you get 6. Take away 2/3, which is 5 and 1/3, which gets me 16/3. And technically speaking, and as far as WebAssign is concerned, that is okay. That is the correct answer. Has anybody got any ideas what I might do to just write it slightly differently? I'm using a style point rule.
No idea.
Put the inverse e in the denominator.
Just that. The original expressions didn't have negative powers anywhere, right? Now, would that be wrong? No. That's just a different version of the right answer. In the same way, I wouldn't typically, I hope you wouldn't do this either. Suppose your calculation ended up being that. I would hope that you would think of it like that, right? Well, if somebody gives you e to the negative 3, all I'm doing is saying, it looks nicer like that. I don't have an extra step. That's as good as it gets. Now, that's really all I'm doing in the style point world, which really says negative powers should be avoided whenever possible. And so if you see a negative power, even if it's a simple one, it looks good just to fix it. Well, this is question 5. and I'm going to show you because it's very visual. It looks like this fella. We want to find the area between the curve y equals 3 over x and y equals 3 over x squared and the line x equals 6. And one of these 4 pictures is the right picture. And you have to figure out which one of these 4 pictures is the right picture before you can then go and do the question, which is find the area of the region. Now, this is going to be a f of x take away g of x guy, right? It's going to be a guy above and a guy below. But there is this picture, there is this picture, there is this one here, and then there's this one here. But only one of those 4 guys is the correct picture. If I shrink it down to the point where you might be able to see the 4, which is here, you probably can't see much else. Any ideas which of those 4 pictures actually represents those 2 curves and the line x equals 6?
Would it be the first one?
So you would put your dot on that one. I'm going to make this a little bit bigger. So you're saying that one, right? Well, it could have been the right answer. So I'm going to do the Sherlock Holmes thing, which is I'm going to kick out all the ones that don't work, and then whoever's left must be the right answer. So keep that one in mind. Why is this one, number 2, definitely wrong? How can I tell, just by looking at these equations and this graph, why this one can't possibly be the right answer?
I feel like it would have a negative number.
Right. If you plug any of the numbers, x equals 1, 2, 3, 4, 5, and 6, won't 3 over that number and 3 over that number squared, won't they be positive? So what does that tell me? It tells me that both these curves have to be above the x-axis. So kick out 2, kick out 3. Now, in a minute, I'm going to put it into the calculator, and that's fine. But, you know, if you can do it without the calculator, it's quite a good learning experience. Now, that means it could be the one that you chose, or it might be this one here as well, because they're both positive, right? What do you know about 3 over x and 3 over x squared as x gets bigger, right? As it goes 1, 2, 3, 4, 5, 6. What do you know about the y coordinates? Don't they get smaller? Isn't this the picture that they both get smaller? So without using my calculator, I figured out that the only one that fits the fact that these have to be positive and that these guys get smaller as you travel along the x values is this one. And I'm going to do those guys in the calculator right now. Oh, let's show you me doing it. So, first guy is 3 over x squared, 3 over x. Second guy is 3 over x squared. Although you can't see it now, the window did start at 0 and it finishes at x equals 6. So if I do a zoom fit on that, and it doesn't start at 0, I apologize, it starts at 1. And I'm going to come back to you and show you why it's 1 and not 0. So I'm drawing the picture of what that looks like. And what I didn't pay attention to, and I should have, is that at x equals 6, it stopped. But didn't that guy there, that guy there is 1. So the integral is from 1 to 6. The fella on the top, take away the fella on the bottom. Oh, which one of these do you think's the top one? Do you think that's on the top, or do you think this is on the top? Okay, let's find out. It's in the top. So the area is the integral from 1 to 6. The guy in the top, take away the guy in the bottom, dx. And I just pulled out of my hat that this was 1 and not as I originally said 0. How can I find this x coordinate? Because it could have been 2. I guess it could have even been a half. How do I find out where these two curves intersect, and therefore, how do I find the 1?
Can you repeat
In
that question?
algebra, in algebra, how do you find out where two curves intersect?
A system of equations?
So what do you do is take the equation of the first guy and make them equal. So two curves will intersect. So if you have a question, area between two curves, and you want to know where the intersection point is. Right? Now, sometimes it's easy to do if you've just got the graph in front of you, right? You can look at the, you can look at the coordinates and tell it's 1. But if you want to find out algebraically, you make both equations equal to each other and you solve. So in this case, cross multiply. Subtract 3x from both sides. Take out a 3x. And there's your guy. I'll take this just a little bit further and then I'll stop on this one. What's the antiderivative of... Oh, you can't see it, sorry. Don't know what I'm writing down here. Oh, I thought I was. There we go. What's the antiderivative of 3 over x?
Three times the natural log of x.
Correct. Now, if you want to find the antiderivative of this guy here, you'd have to do something like this on the side. You'd have to rewrite it as a negative power. Then you can find its antiderivative. Add 1 to the power and divide by the new power. And then you make it look pretty. So the antiderivative of this guy is positive 3 over x. Well, we're almost finished. Take it the full step. So 3 natural log of 6s plus 3 over 6. Take away 3 natural log of 1s plus 3 over 1. Three natural log of 6, add a half, take away. What number is 3 times the natural log of 1?
0.
So take away 0, don't care. Take away 3. So that gets you 3 natural log of 6. Take away 7/2. And that's as good as that's going to get. I'm going to show you another one of those 4 picture things, and we'll see if we can figure out who the answer might be as a picture. We want to know the area between x equals this ugly guy and x equals that ugly guy. Okay. Now there are 4 pictures here. One of these 4 is the right guy. You can certainly put it into Desmos, and that's what you probably might have to do if you're not very good at what I'm doing. But it's so much better if you can do it without that. Okay, so let's get rid of a couple of these questions, a couple of these pictures. 2 of these guys can't possibly work. And I know that because of the way the equation is written. It's x equals a function of y, right? This one can't work. Isn't this one got a vertical strip? That means it's, you know, y equals x cubes. And this one doesn't work. So it's one of these 2 guys. And if you plug them into Desmos, you'll find out which one of these 2 guys it is. But let's suppose I want to try and find out without Desmos. Take this fella here, 63 take away y squared. If I wanted to know where this fella cuts the y-axis, oops, sorry, where this fella cuts the x-axis. If it's 60 something, then it's this picture. And if it's only 30 something, it's this picture. So how do I find out where does this fella cut the x-axis? Well, I make x 0 and I solve. What do you get? Well, if you make x equals 0, you get 63 on both sides with a negative. 63 over 7, take square root of 63 over 7, you got your answer. Now, how would you do that if you wanted to see it so that you could figure out all the things? Let's do, oh God, we're getting short of time. Let's see if I can do another Desmos. Clear this fella out. Clear this guy almost out. 63 take away. I think it was 7 y squareds. And that's the first one. Ooh, well. Eek, that's not very pretty. And then the other one is going to be 7y squared minus 63. Now, the Desmos has got a really awkward scale here, which you should be able to just change. Does anybody remember how to change the scales?
It's the little wrench at the top right.
Right. And so you can go in here and we can change the y values to, I don't know, some reasonable like -10. And I'll just take this guy and I'll change it to +10. Now, if I kick out of this, there, do you see it looks much more natural? And you also get a clue. Isn't the red guy this fella and the green guy this fella? So you're going to do the equation of the red guy, which is 63 minus y squared, subtract the equation of the green guy, which is this fella. Now, wouldn't it be really helpful to know where they intersect, right? Because you have to go from that guy to that guy. Now, if I put my mouse pointer on it, can you see the coordinate 0, 3?
Yes.
I can see it, but it's very faint. Right? Doesn't that make the y value there 3 and the y value here -3? So you put all of that information together. The area between these two curves is y equals -3 to 3. Red curve first, which is 63 take away 7y squared. Red curve first because it's on the right. Take away the green one, which is 7y squared, take away 63. And now I will return to show you what I've just written. Because if you set it up right, to me, that's the hard part, right? If you can set this up, can't you, isn't it just a normal integration, right? So what would that look like? Well, I would probably do an extra line before I do anything else. Take away 7y squared, add 63. And that would be -3 to 3, 126, take away 14y squared. Now, as big as these numbers are, would you agree that is just power rule and plug and jug? If you set up the integral, typically everything else is pretty straightforward. So setting it up is the key here. And isn't Desmos your friend? It allows you to do curves that you couldn't do any other way, like x equals y cubed and things. And it also allows you to find where the intersections of curves are, so you know the start and the finish values that you're going to use. Now, there's just one last thing that we need to do to kind of cover every permutation. And it's this fella here. We're still going to find the area between two curves. This is y equals f of x. Here's my next guy, y equals g of x. And let's suppose that we're starting at some point here, which I'm going to call A, and we're going to finish, say, at some point here, I'm going to call it B. So the area between the two curves looks a little bit like some weird glasses that somebody might wear. Now I'm going to give this guy a letter C. So that has an x coordinate of C, that point of intersection. The area between these two curves isn't the integral from A to B, f of x take away g of x. And the reason why that's not true is, isn't there a switch over? On this end here, this piece here, isn't the blue guy on top and the green guy on the bottom? But once you get to C, don't they switch places? And the green guy is on top and the blue guy is on bottom. So whenever you have to do an area between two curves and there's a crossover, which is what I call the situation, right? There's a crossover. You actually find two separate integrals that you add up. So you find the integral from A to C. Blue guy, which in this case is f of x, take away the green guy. And then you find the integral from C to D, but in this case isn't the green guy first and the blue guy second. Does that make sense, that that's how you would tackle what physical area these two add up to, that you would have to do a switch over on who's first and second, depending on if you're getting this piece or you're getting that piece. Does that make, logically, does that make sense? That intuitively, that makes sense? Now, what could go wrong? Well, suppose you didn't even draw a picture. Suppose you just said, oh, it's dead easy. First curve, take away second curve, and I'm going to go from 5 to 10. And if the answer's -2, I'm just going to put in 2 because that's how I fix the other ones. Well, if it's a single curve above and below, won't that careless technique work? Because if you get it the wrong way around, you just get -10 and you call it 10, right? And it works. But when there's a crossover, that technique will fail you, right? If you just do the integral from the start value to the finish and you only do one curve, take away the other, right? As a single subtraction, it will never be correct. In fact, you can get all sorts of weird answers. Couldn't you get the answer 0 in some cases? Which would never happen in the other situation. Well, see if this bit was exactly the same size as that. Wouldn't you get 0 if you didn't do the crossover? See, this would be 5 and this would be -5 and they'd cancel out. Couldn't this be 5 and 7 and you could get -2 as an answer?
We can't see.
Couldn't it be 7 in the first piece and 5 in the second? Right, all these combinations. None of them are any good to you because they're all wrong. The only one that works is finding these two separate and adding them up.
I can't see which ones are going.
Which means, oh, darn it in space. There, it's that window issue I've been having all day today. Right, sorry for, you're getting a very quick summary of the same thing I just said. There is a crossover, right? So you have to find blue guy take away green. And then from C to D, it's now green guy take away blue. And you must do it this way. If you just said, oh, I'm just going to find the start to the finish, and I'm picking the first one to be F and the second to be G, right? That will never work. It won't even be the negative of the answer. It'll just be our number that's wrong. And so you need the picture. You also need to find out where those guys intersect. But won't that be Desmos's job most of the time? Okay. So I'm going to try and put together a quick example of Desmos helping us to do a crossover question. While I'm getting myself kind of organized, you want to say hi. And so you can get your attendance for today. Now I'll be playing about with these for a few minutes, so. That's better. Okay, and I'll do my second curve now. Tweak that a little bit. Yeah, that's better. And my second curve's going to be looks good. I just need a little tweaking on this one. Squared, I want something at 2. So what will that get me at 2? 2 is 8, 13. So 2 take away 8, 6. I think you should do a -7 here. Oh, darn it. 4. Right. Two. Darn it, not quite what I wanted. Make this 4. Yay, got one I wanted. Right. So, do this guy up. Suppose you wanted to know the area between these two curves. Right. Oops. Starting at 0 and finishing at 5. Right. So starting at 0 and finishing at 5. Do you see that there's a crossover here? So I'd be getting this piece, and then I'd be getting that piece. And right at the crossover, you see the x equals 2. So I would do an integral from 0 to 2. Dark blue take away light blue. And then from 2 to 5, light blue take away dark blue. Now notice the dark blue is above the light blue. And then over here, they switch places. Light blue above the dark blue. And the point of intersection is 2. So you would set up that integral between those two separate integrals, and you would be finished. So I'm just writing this down, and we'll call it good. So the question I set up there was find the area between this quadratic and this quadratic from x equals 0 to 5. We found out that there was a crossover at 2, so we do the integral from 0 to 2, and the guy that goes first was this one. Take away that guy. And then you add from 2 to 5, the rest of the journey, and these two switch places.